All right, good morning, folks. Today we are going to talk about something you learned hopefully a few times by now, and that is some atomic structure stuff. This isn't chemistry class, this isn't physics, so don't worry. You're not going to be balancing equations or any of that crap, all right? I never really enjoyed that much either. Chemistry is something that I really appreciate in retrospect. The math at the time really turned me off. And the fact that I didn't spend a whole lot of time studying, too. But I get it now. At least I get it a lot more than I did back then. And it is really important. And it's really kind of cool and neat, too. And then when you get into older, like higher level chemistry classes, they kind of tell you, well, you know what we told you in 101, that's not really true. Like electrons really blew my mind when I learned about electrons formally. But they have to teach you the foundation, right? The rules before you could learn all the exceptions and the oddities. So, you know, that's what you get in the intro level classes. And then, like I said, a little later you find out, okay, well, I know we told you this, but we're not even going to get that deep, all right? Occasionally we get a little deep, but, again, no balancing equations, so don't worry. All right, so we're going to start small, right? An atom. What's an atom? Well, an atom is the smallest piece of an element that still retains the properties of said element. You could call it a particle if you wanted to. That word floats around here and there. The important bit, though, is that it is the smallest piece that still would be recognizable, okay? Smallest piece of sulfur that is still sulfur. The smallest piece of silver or gold or whatever.
The sulfur is an element.
Yes, sir. Yep. Now, most of you know, of course, we could get smaller. What are some parts of atoms? Nucleus. I heard neutrons.
Gluons.
So we're going to get, that's my next question. All right. So usually I hear protons, neutrons, electrons. Some of you are aware that some of those are even made up of stuff. Okay. And we're going to touch on that a little bit as well. So this whole smallest piece of something is really kind of relative. I use a Lego analogy a lot, okay? And the smallest Lego you can get is that one square, one thickness, right? You would think that would be the atom, but it turns out, no, it's actually a good bit bigger because we do have to get down to crap. We don't talk about gluons, but we do talk about quarks, all right, which are parts of, well, you'll see. I don't want to jump ahead of my slides. So it's all relative, so to speak. So that's why this last bit is so important. So we already more or less got these, protons, neutrons, and electrons. And again, I'm sure you walked in the door knowing that, or at least were refreshed relatively quickly. Believe it or not, this turns into 9 questions on the first test. How the hell do you do that? Well, you're going to learn 3 things about each of these, all right? And more or less, they all do show up as questions. So we're going to learn about, or try to remember, the mass for each of these. We're going to try to remember where they live. And we're going to try to remember what their charge is. All right, and again, you should know this, but remembering that you know it is the hard part. So first we got the protons. Whoops, didn't mean to skip it. First we got the protons. So subatomic particle that contributes, I should have asked you this. This was supposed to be a query thing. I'm a little foggy this morning. Contributes 1 mass unit. All right, what is 1 AMU? Well, we'll see that in a couple minutes. It's not a number you need to memorize for this class. But it's really no different than a gram or a millimeter or a milliliter. It's just a unit. All right, don't be scared just because we're getting really small. So what's its mass? 1. All right. What's its charge? Pretend you can't see that. What's the charge on a proton? Yeah, positive. Awesome. All right. Proton's positive. PP. And where do protons live? Nucleus. Good. All right. Somebody mentioned nucleus earlier. I don't really think I have a slide for nucleus. Nucleus is that center portion of the atom. All right. For those of you that don't recall. And it's where you're going to see, they always sort of cliche-ingly say, that's, if you allow me to conjugate as such, that's where the 99% of the mass of the atom is in the nucleus. So the proton is one of the things that live there. Neutron, all right, contributes one more mass unit. What's the charge on a neutron? Neutral. No, it's tough because it's got the N, right? You want to think NN because we just had PP. But we got a different one that's going to be negative in a minute. Yeah, neutron, neutral. So it even shares the first 3 letters, right? The first 4 letters. Well, hell, first 5 letters. All right. Neutron, neutral. They really just changed. So they weren't really trying when they named this one, huh? So the neutron gives 1 AMU, and it puts no charge into an atom. And where does it live? It lives in the nucleus as well. All right. So an electron. The electron is a negative one. In fact, some of you might remember that it's usually abbreviated with the lowercase e and a negative sign next to it, right? It does not contribute any significant mass. And again, one silly little word is kind of really important. In this case, is the word significant. You guys probably haven't dived into your lab homework yet. All right. But one of those, in the vocabulary section there, we talk about mass and matter. All right? And yeah.
It's pages 1 to 7, right?
Yes, it is. Yes, it is. We talk about mass and matter in the first part of that. And, this is by no means a formal definition, but mass is a sum of your matter, right? And matter is basically a measure, anything that has mass and takes up space. So they're interconnected, they're intertwined. So if we say that electrons are massless, well, we're saying that they're not matter, and they certainly do matter. At any rate, so we have to say no significant mass. They have some mass, but you can throw a whole herd of them into the atom, and it won't affect the mass at all. Okay, it will do things to the charge. Don't get me wrong. But it won't affect the mass. And speaking of which, who could remind us the difference between mass and weight? Another one of your lab questions. We kind of use them interchangeably, but we probably shouldn't.
I'm trying to think. Weight is how much something weighs, but mass is the amount of matter in a certain space.
Yeah, but what's the difference? Help him out, somebody. He's on the right track. He's just not in the station yet. Oh, I can see your hand. We don't have to do hands in here. You guys can just, don't be rude and shout over each other, but you can just talk. Go ahead. Yeah. What? Go ahead. Mass doesn't. Why can weight vary? Gravity. There we go. So, weight is gravity's effect on your mass. That's the difference. You know how they say you could go to Saturn, and I forget if you get way more or less there, but we'll say you weigh less there. Okay. I think it's a lot more, though.
Saturn is the one with the rings, right?
Yes, sir. So they say you weigh more on Saturn. Well, you didn't gain weight on the way to Saturn. It's just that they have a different gravitational pull. All right. You go somewhere that you weigh less on the moon. Well, unless you lop off a body part or something along the way, you still have the same mass. You still have the same amount of matter. So that's why weight can vary. All right, weight is gravity's effect, and that's, like I said, in your labs as well. Anywho, back to this. So the electrons are located outside of the nucleus, okay? And like I said, this is one of the things that really blew my mind when I started reading about it. And if you like this kind of stuff, it's Electron Wikipedia page is fairly interesting, actually. We had to all learn the shell structure, right? You guys remember the shell structure? 1s2, 2s2, 2p, whatever they were. Oh, I hated that. But you need it to balance equations and to make everything work. I believe that's, was that the Bohr model? It had a name. I took chemistry a long time ago formally. But you need it, okay? And I suppose if you take a snapshot at any given moment, you're going to see something resembling that. Well, when you get a little further along in chemistry or physics or some related field, you'll learn that that's not the case. Electrons are actually what, they say? They're in a what? A shell. Well, yeah, the shell. And that's those wonderful rings. They say that, I'm just looking for hands. They say that they're a cloud. Okay, the electrons are a fuzzy little cloud. And more so that they blip in and out of existence. Your electron could be, in you for a moment and in your cat a minute later and then over in your glass of milk. All right, they're really funky things. Really weird. But then you got to start, if you want to believe that stuff, you don't believe science, but you know what I mean. You got to go into the particle physics, and then you start talking about strings and all those wonderful theories, and it gets weird really quick. But that's what the folks that think a lot about this stuff think about electrons. So shell theory be damned, okay? But again, you got to learn it or you never balance those equations. That's why we teach it that way. So outside of the nucleus, fuzzy little herd of mosquitoes. So I told you we'd learn more about a mass unit, but first I just want to make sure you guys got all 9 points, okay, on this first test about those 3 things. So proton, charge of? Positive, good. Neutron?
Neutral.
Electron?
Negative.
Who lives in the nucleus? Protons and neutrons. Where do the electrons live? Outside, okay. And what are our charges? Swept it up on you there. All right, proton is?
Positive.
Oh, did we do this? What are their masses? I'm sorry. So protons and neutrons have measurable mass, and the electrons not. Okay, good. We got it down. So what is an AMU? Down here. All right. It's tiny, but we're talking about atoms, right? So we should expect that, I would hope. You know, if it's got a negative, which way the decimals move in, or which way the zeros are going to go in at any rate.
To the left? Yeah, to the left, right.
To the left, right. That's why we're watching a movie today. We're going to watch a little movie about this. But again, it's a teeny tiny unit of measurement, but don't start getting in a little later. I don't know if we're going to do cosmology this semester, but we might start talking about light years, and people get all freaked out because we're dealing with really big. It's just another number. All right. Don't let the units scare you. So AMU, atomic mass unit. I do have a slide for nucleus. How about that? So it's a central portion of the atom, contains 99% of the mass, and it's where the protons and neutrons live. We good? And again, for those of you frantically trying to write down everything that's on these, this is why, I know I didn't do it yet, this is why I give you the slides, okay? And then you could actually write down some of the other stuff that comes out of my mouth. So I know we sometimes go through these slides a little quicker than you can write. I apologize. But I got tired of the from you guys, again, understandably, as I was switching slides too quickly. So they'll be up there for you. Feel free to trust in the fact that a little later today you can print this guy out, okay? I haven't heard any sighs this morning yet, so that's good. But
If you want.
there'll be a time, I'm sure. So I've been using this word rather freely, all right? And I've learned, if I've learned one thing in my 20-some years here, it's don't take anything for granted, all right? I went, 3 or 4 lectures. Remember I told you sometimes I talk about cosmology? I went 3 or 4 lectures, and then finally somebody raised their hand and said, wait, what's a galaxy? And I just assumed that everybody knew what a galaxy was, but that wasn't the case.
Galaxy and universe are not the same.
Huh?
Galaxy and universe are not the same.
Correct. Correct. One is inside of the other. So I don't want to take anything for granted. Here, I've been using the word subatomic. All right? Sub means below. So subatomic is below atomic level, below, that's smaller than an atom. Think about some other words you know. All right? Submarine.
Yeah.
Substandard. Subsidence. I don't know if that one works. But, so you get the idea. It's prefixes and suffixes. Everything's a little bit of Latin English in the end, really. So subatomic, you can spell it however you want. First one looks kind of weird, but coworkers has always bothered me because I always read cow first instead of, so, you know, if you want to use a hyphen, feel free.
Error in parsing.
Yeah. Huh?
Error in parsing, I'll say.
Ah, there you go. It's your call. Or you could put a space. See, it looks weird with a space, though, too. So.
No.
All right. Speaking of grammar and such. Elementary particles, not elementary. I don't know why. All right, because you didn't go to elementary school. You went to elementary school. But whenever we say elementary particle, see, I just did it. We say elementary. So this is a subatomic particle. See, there was a reason for that previous slide. I told you a little while ago that there were some smaller stuff. And there's some other bits that we don't talk about in here still, okay? But these are fairly important. So an elementary particle is a particle not known to have substructure. So at the moment, we don't think they get any smaller. Remember, though, that we said that about the atom? And we said, oh my gosh, wow, there's parts that make up the atom. This is as small as it gets. We said that for a couple decades. And then they said, holy cow. Some of these guys are made up of other things. So, at the moment, these are the fundamental building blocks, the basic building blocks. These are the smallest Lego piece. This is one nub, one thickness of Lego. And we got two kinds. We got quarks and we got what we call leptons. I don't really use the word lepton too much because the lepton that we're worried about is an electron. We're already just going to keep that word. So we're going to tell you that we got quarks and electrons. Okay, that sounds a lot like lepton anyhow. But so electrons just are. There's no pieces, parts to electrons that we currently know about. But the quarks make up the protons and the neutrons. And quarks are kind of really funky, actually. I mentioned going to the Wikipedia page for electron. The quark one is even odder. They talk about flavors with quarks. They have spin. It's a whole new interesting world out there. So everyone's into multiverse lately. It's starting to get into that realm. Okay. So elementary particles. Again, in here we primarily care about quarks. There's another word we don't need to worry about too much, but just want to use the proper terminology. Hadrons. All right. The whole world learned about hadrons, oh gosh, it might be 10 years ago now. They built a new particle accelerator in Switzerland.
Yeah, you said that.
And yeah, I talk about this every time I give this lecture. It was CERN, C-E-R-N, Center for Lord only knows. And it's probably in Swedish too. So, but they got really cocky and they were looking for the God particle. And of course, every time you say that, you freak people out. It was the Large Hadron Collider. There was even a Large Hadron Collider rap at the time. It was insane. You guys were probably not paying attention to it, but I'm sure it's still on YouTube. So everyone learned the word hadron, okay? Well, we've been doing this underneath Chicago for like 75 years, and no one has cared at all. But the impression was that they were going to open up a black hole in Switzerland and unicorns and were going to come out of it, and it was going to get really weird. And the funniest thing is when they plugged it in, you know that noise Pac-Man makes when you die? It kind of did that. So their God particle. Isn't that funny? So it's working now. It's amazing. The only thing it is it's bigger. It's the largest one we've ever made. And it's a racetrack. All right, you're going to see one in the video we watched today. And unlike auto racing where no one, wants to see a wreck, yeah, right. We're trying to get these things to smash into one another. And the idea is the bigger it is, the faster they can go, and the bigger the bang will be when they hit. So that's we're trying to break these things down, okay? So that's what a hadron is. It's these composite structures here, which you previously knew as protons and neutrons, all right? But at any rate, so when you smash those into one another, you get neutrons. You get quarks, all right? And I'm sure they're trying to smash quarks into one another as well, see what they get. No unicorns as of yet. So. And as I said, lepton is just another word for electrons. Neutrino is another one that some of you have heard about, but again, doesn't really pay any mind to our class. So electrons just are. Protons and neutrons need to be made. And that's where it gets weird if you do go back to the Big Bang and start thinking about that stuff and the periodic table being built one element at a time from protons and neutrons smashing into one another. All right. So how long have we known about all this for? Well, oh yeah, go ahead. Do and don't what? Quarks are used to form. Good question. Because I suppose you could argue that an atom is a composite structure. I'm not sure if that's where you're going with this or not, but just want to be clear. All right. I didn't know if you were overthinking in this early in the morning or not. All right. No, so quarks do is the easiest answer to your question. Because quarks make protons and neutrons, electrons just are. But whether you were going down this rabbit hole or not, you could argue again that when you put those together, you get a composite structure as well. So yeah, excellent point you didn't make. But, all right. Okay, so unfortunately, I've been teaching long enough where I was able to say it hasn't even been 100 years yet. And then one year I was able to say it's the 100th anniversary of we discovered an electron or an atom. And now I say it's over 100 years. So Rutherford, all right. Ernst. I wrote Ernest in here. I'm pretty sure it's Ernst. We've known about this. I think it was Plato, actually, that put forward the idea of some tiny particle that everything's made of. It wasn't Plato, it was Socrates. It's one of those guys. I think it was Plato, though. So we've had this concept as long as we've been thinking. All right, and they probably tried to put one on a cave wall, too, but we just didn't know what they were thinking about. But he wrote his stuff down. So we've always had this concept. And it's actually sort of been over here on the side the whole time here, this lovely ball and stick figure. It's not blueberries doing something really strange. This is sort of a classical depiction of an atom, and it's really easy to build in the classroom, which is why you see it sometimes. You may have made one out of raisins and toothpicks or mini marshmallows and toothpicks at some time in your life, depending on your science teacher. All right, but that whole concept we really didn't have in, like I said, a little over 100 years now, which is as much as we know about it, as much as you guys at age, kindergarten, first, second, third grade, whatever, know about these things, they introduced that idea. It's kind of crazy that we've only known that for about 100 years. 113. Here's a more traditional model as well that you don't see. You see it everywhere. But this is your very atomic age kind of thing. Okay, 40s, 50s, 60s. This has the idea of those electrons moving in rings for students to memorize. It gives you the idea of the nucleus there. And like I said, this is another way. But again, barely over a century we've known about this, so 113 years. Okay, so we spent the first half of this lecture talking about atoms, and we told you that they were the smallest part of an element that still retained the properties of an element. Remember that definition on the opening slide there. So now we're actually getting around to reminding you about what an element is. There's 100 and some odd of them on that periodic table that I mentioned a minute ago, and if I'm lucky, we'll be showing you a picture of one in a moment. You've all seen it, but just to refresh your memory. Unfortunately, this definition doesn't entirely work so well in geology. It's a real definition, it's true, but you remember how I told you in the lab, when you're out there Googling the definitions for your vocabulary words, try to make sure that it is relevant to the class that you're in, and so on and so forth. So a substance that cannot be broken down into other substances by ordinary chemical methods, all right? That's our working definition of an element. At the time, we had like a Chemistry 100 at the school. I don't even think we offer that anymore. It's just like chemistry for fun kind of thing. If you had no chemistry in high school, but you had to get through it, they put you in there. If you needed, I don't even know if it didn't even have a lab, so I don't even think it did a gen ed elective for SUNY. All right, it was just like physical science kind of thing. So I grabbed their textbook. I'm like, I want a basic definition. And I checked an actual, Chem 101 textbook, got their definition. This is the definition. Here's my problem. Here's our problem. You guys are in geology now, so it's your problem. You ever hear of radioactive decay?
Yes.
Kind of important in geology. Why do we use it? Yeah, to date stuff, all right? So all those jokes about geologists dating rocks come from. We used radioactive decay, radiometric decay. There's a couple words go around. Radiometrics, usually the most common. Well, what's going on in that? An element is giving off energy and breaking down. And since it happens in nature all on its own, I would call that fairly normal.
Is that the same thing as carbon dating?
Carbon's a little different. We're actually going to do, I just put it in the last couple semesters, we're due geologic time in a PowerPoint, in a PowerPoint, unfortunately, in a lecture or two. Carbon dating works a little differently, but you guys hear about it more because they use it for a lot of stuff you'll see on Discovery Channel and National Geographic Channel, all that stuff. They use it for more recent stuff. And we will talk about it. So my point being, we rely on the fact that a handful of things break down into other things. Elements break down into other elements. Uranium to lead's a big one everyone knows about. All right, there's rubidium and strontium. There's something in thorium. I forget. It might be thorium and strontium actually. But there's a handful of what we call decay series. All right, and we know how fast they decay. It's rote memory at this point. Okay. Yet this is still going to be our working definition. All right. A substance can be broken down into other substances by ordinary chemical methods. Asterisk. Oh yeah, except for when we count on things to decay. Now, there it is. All right. Hydrogen, helium, lithium, beryllium, boron. I always forget about boron. Carbon, nitrogen, oxygen, iron, neon, so on and so forth. There's 100 and some of them. Some of you actually know why these guys are down here. They go up here, right? I never figured that out in chemistry. I'm sure I was told. I was probably doodling. The main thing that's constant here is that they are, for the most part, numbered in order. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, so on and so forth. We're going to learn about those numbers in a moment. We're also going to learn about, you can't see it, I know, down underneath, there's a much larger number, typically a decimal. Okay? We're going to learn about that as well. I bring this up because, again, I promised you, you're not going to be writing balancing equations, writing equations, but you are going to write some formulas when we get to minerals, all right? And some of them are easy. Sulfur, what's in sulfur? Well, sulfur's in sulfur. But orthoclase feldspar got like 6 things in it. And it's kind of helpful. I never quiz you. I never say what is, Ne. We don't go there. But it's kind of nice that when you're writing down AlSiO, Fe, whatever, which is an aluminosilicate with iron in it, all right, that you know that, oh, Al is aluminum and Si is silicon, and so on and so forth. So this is why we bring this into the mix. All right. We're not there yet, though. So you probably didn't notice, but when I was talking about atoms, I was very careful not to list something like salt or even water as the smallest pieces part of an element. Remember that conversation? And I said, so you've got the one piece of sulfur that still looks like sulfur, one piece of silver, or whatever I said back then. Because if it's what we call a compound, something that's made up of two or more different things, we have a different word for it. All right, you've heard this word. It's called a molecule. We'll have a slide for it in a minute. This is the magic, I think, that really would have caught my attention when I was sitting there taking chemistry. Compounds are freaking amazing. They're magic. They're not magic, I'm sure. But to me and to some of you guys, it's right here. You combine two or more things, but you get properties different than the individual elements. Now, some of you could argue that this is like baking, right? You're making brownies, and it's this nasty goo, but we eat the dough, so it's not that nasty. But brownies to, brownie dough to brownie, that's kind of magical. Let me give you a better example. It's almost like this is a in processes PowerPoint. Some of the stuff that I thought was here isn't here. All right, so on the right, anyone want to hazard a guess what we're looking at on the right?
Is that quartz?
No, way softer than quartz. And cubic. So no, it's about the softness of calcite, but it is not rhombic. These are all words that will make sense in a couple of weeks, don't worry.
Not sodium chloride.
Well, what do we call sodium chloride?
Salt.
Salt, yeah. So that is salt, all right? And crazy thing about salt is whether or not you go and buy some really fancy salt, or you go to McDonald's and buy a packet of salt, or wherever, it always has those same properties. Not only is it just salty, all right, but it's cubic like that. So anyhow, you jumped the gun on me. What's salt made of, you guys?
Sodium and chlorine.
Sodium and chlorine. Okay. So I reckon that you guys don't know a whole lot about sodium or chlorine. You might know a little bit about chlorine.
Pool water.
It is pool water. All right. But before we use it to cleanse our pools and whatnot, we use it to do some really nasty stuff. Chlorine's on the bottom left here. Chlorine is a very poisonous yellow gas. All right. Sodium, and it's good that he didn't say sodium and chloride. Chloride is a confangled mess. The element is chlorine. All right. We have the same problem when we talk about silica and silicon and all that stuff. There's a couple different endings. So anyhow, sodium is a fairly soft, metallic-looking thing that happens to be incredibly flammable. All right. So you take a soft gray flammable metal and a green poisonous gas, you mix them together, and it makes your French fries taste good. Who the hell would have thought that? Okay? That's what I'm talking about, the magic of compounds. Okay? Something happens when you mix those things together. Again, it is way above me. But something special happens, and that's really neat about compounds. And like I said, I think if my teacher had focused on that a little more and less on the math, but another one is water. What's in water, you guys? H2O. All right, so H is what?
Hydrogen.
And O is?
Oxygen.
Oxygen, awesome. All right, so arguably, let's just call those both gases at the moment, right? So you mix two gases together, and not only do you get a gas, we have something called water vapor, right? But you get something that could be a liquid, and something could also be a solid, all at normal temperatures, normal surface temperatures. Again, that's pretty great. Now, water is super unique. There's very few things, if anything else, that does all three states of matter, all right, under normal conditions. But, yeah, so compounds, very impressive.
Wait, liquid, solid, gas.
Huh?
The three states of matter, liquid, solid, gas, right?
Yes, sir. Yes, sir. Also, one of your lab homeworks. So I started talking about this a moment ago. This is almost like a pluralization rule, all right? Not entirely, but when you use atom, when you use molecule. So when we're talking about a single ingredient, it's an atom. Again, an atom of sulfur, an atom of gold. But when you have a compound, sodium chloride, like we just talked about, H2O, you would never say an atom of water, right? It doesn't even sound right. It's a water molecule. And you've been trained, since day one to use that word, but there's a reason why when we move up to a compound, we use a different word. There's no atom of air. There's an air molecule. Again, that sounds right because you've heard it forever. So they have the same definitions until the very end. So a molecule is the smallest possible unit of a compound that retains the properties of that compound. For those of you that got lost in my ellipses there at the end. All right. So remember the periodic table, and I told you we were going to spend some time talking a little bit about that. I have no idea why the molecule thing was in the middle of that. That's kind of what threw me off a moment ago. So we got a little snapshot there in the corner of some elements. And you can see hopefully a little better the single number in the top, and you still can't read the smaller number in the bottom. But I want to talk right now about that number in the top, the one that is essentially in order. Hydrogen 1, helium 2, lithium 3, beryllium 4, so on and so forth. All right. That's called the atomic number. You've heard this, but not for a long time. What might be new to you, or what you might have forgotten about the atomic number, is that it is actually a proton count. That's the important part. And as such, this is what defines the element, the number of protons that is in it. Carbon. See the number 6 above it? Carbon has 6 protons. Nitrogen has 7. Oxygen has 8. And yeah, not to Sesame Street it up too much, but it is as simple as putting one more Lego on each time you're adding, another proton. And if you take 6 protons and add one more to it, you're going to turn carbon into nitrogen. It seems kind of crazy that it works that way, but again, at a Sesame Street level, that is. Those of you that know a lot about chemistry, there's so many chemistry heads, I apologize for my, slandering at times about chemistry here. But I talk to the middle to the lower end of the road in chemistry knowledge because that's where I spent the majority of my life. But definitely there's a handful of you sitting in here that know more about chemistry than me. I'm quite confident in that. So again, I apologize if I heresy every so often. All right, atomic number. It's the top number, and it defines the element because that is the number of protons in it. And here's that periodic table again. So the idea being that we're just adding protons as we move from the left to the right and down. So you jump all the way down to PT. What are we picking? Platinum. Okay. Platinum has an atomic number of 78. How many protons are in platinum? 78. All right. It's that straightforward. Do you need to memorize that? God, no. All right. If you use this enough, would you? Sure. But it's important to know when you're looking at a periodic table what it actually means. So the next thing we need to focus on is something called the atomic mass. Remember we talked about atomic mass at the very beginning. This is the number at the bottom. All right? And as it says here, it is the sum of the protons and neutrons in an element. It doesn't take a whole lot of time staring at one of these things to realize that 9.9 times out of 10, 9 times out of 10 we'll say, the atomic mass is twice the atomic number. So let's go back to carbon. All right, carbon had an atomic number of 6, and turns out it has a mass of 12. Yes, there's a decimal. We're going to ignore that. Nitrogen, atomic number 7, mass of 14. This is because, and again, Sesame Street rules, protons and neutrons tend they like to be together. And they like to have balance, okay? So you tend to get just as many neutrons as you have protons. So if you have 7 protons, you're going to more than likely have 7 neutrons, thereby doubling your mass. Doesn't take long, however, if you stare at a periodic table long enough for some reason, to realize that that isn't always the case. I'm going to make one up, but let's say, well, let me see, do I actually provide myself with? All right, selenium. Selenium has an atomic number of 34. What should its mass be? 68, by the rule I just gave you, right? Selenium's actual mass is, I believe that's a 78. Breaks the rule, right? So what are the two things that have mass? Protons and neutrons. So how did they get selenium to 78? You need a hell of a lot of electrons. Remember, electrons are essentially massless. Arguably, you could. So that's not an option. We got two things that have measurable mass. Yes, ma'am, I think you were first. More neutrons. All right, what were you going to say?
I was just going to say the protons and neutrons are the same.
Which is their, what are we adding? Neutrons or protons?
Protons.
Protons, and you. Add protons. All right. Should we vote? How many of you think we're adding neutrons to the mix? How many of you think we're adding protons to the mix? All right. Some of you are just staying out of this. There's no points attached. No, I'm not judging you on day one. Why can't it be protons?
Because every time you change the proton number, it's going to change the actual element.
You can't mess with the protons. All right? If you change the protons, you change the element. It has to be neutrons. All right? It has to be neutrons. We've got a word for this. You actually know it. Isotope. All right? So you can't mess with you can't mess with protons because that changes the element. Remember, atomic number is fixed. You add an extra proton, carbon is no longer carbon. It's nitrogen. Brain fart there for a minute. But you could throw a whole bunch of neutrons. If you could get them to stick. And going back to carbon dating question that you had, that's the whole point, is there's different isotopes of carbon out there. And when you're alive, you're, I'll say inhaling, but you're taking in all of them. Once you die, you don't. And some of them break down differently, so they compare ratios of carbon-14 to carbon-12 and all that jazz, which is right there. So an element in which, this is really one of my first PowerPoints that I wrote, so I was still talking fancy back then. Element in which the atomic mass is not twice the atomic number because of a differing amount of neutrons, okay? And again, we dig this in geology because some of these isotopes are unstable. They break down. So it's not just uranium decays to lead. It's a very particular variety of uranium that we want to look at. 230-something eludes me at the moment. But, all right.
Ask that again?
Huh?
Ask that question again.
What was the question?
Something about uranium, I think.
Yeah. Don't Siri me. It's all good. Or Google me. Whatever.
No, I'm just thinking
Yeah.
it's either uranium 235 or 238.
One of them. 238 sounds right. There's a 236 though too. But at any rate, I thought you were going to Google it.
No.
Saw the
I know
phone.
the song.
Saw the phone in your hand. So, all right. At any rate, why the hell did we just do this? You're probably wondering. Whoops. Crap. Exactly. No reason. Why did we just do this? All right. So this is, again, written for all my classes, so I've got a handful of things in here. But I tend to have a holistic is an overused word, and it's really kind of lost its meaning anymore. But a big picture kind of view when we talk about this stuff. Okay. In order for you guys to understand minerals or rocks that are made directly from minerals, you need to understand a little bit of how those minerals are put together. This is not a mineralogy class. You could actually take 14 weeks on learning about minerals. We're not doing that. Okay, but we need to discuss it a little bit for an hour. You're going to spend way more than an hour in lab learning to recognize minerals, don't get me wrong, but the philosophy behind them, the theory behind them. So in order to understand that, you got to understand elements. And in order to understand elements, so we back up. And in this case, we backed up as far as we can go. It helps you understand atmospheric studies. You can read that as meteorology or weather. Pollution. Pollution is nothing more than elements floating around in the air that we don't want there, right? So if you want to understand how to deal with pollution, you need to understand the elements in them. A mineral is composed, as we just said, of one or more elements. And a rock, guess what, is composed of one or more minerals. And what do you think the earth is made out of, right? A whole bunch of rocks. So that's why we did this. And that's how it's related. All right, so that's the end of this PowerPoint, as you saw a moment ago. This doesn't have a chapter. There's some of this in the introduction. There's some of this in the appendices. All right, so if you want to do some reading to back this up, it's not chapter, well, it is a little, introduction is chapter 1. It's a little bit of in there. Chapter 1 in this book is very broad. So it's there. Eventually we'll get to the point where you folks that love to read the books, and you should. I'm not, everyone should. But some of you will get frustrated because we're not in a specific chapter. When we get to minerals, we'll become chapter-based, okay? We've got this lecture. We've got scientific method coming next, which is also, again, in, I think it's in the introduction, probably not the appendix. And then we're going to do this introduction to the Earth conversation, which goes into like 6 different chapters. So again, it's going to be hard to read the text for that one. But I promise you, after that, we'll be doing the mineral chapter, the volcano chapter, the this and the that chapter. Okay? So bear with us. And this is mainly for you folks at home who are possibly just, feeling a little out of touch. I'm talking to my geology class, by the way. If you're hearing this in earth science or so on and so forth, much of this, all of this applies directly to you as well. But just for context, I'm talking to my geology students on campus at the moment. All right, you guys have any questions before I wrap this up? Julio. All right. We're not done, though. As I said, I did want to show you a feature presentation that kind of ties a lot of this and your lab stuff together. And they tie all this stuff down. That's not happening. And not helpful because it's shooting at the floor now. All right, well, I'll make sure you can hear it. So this is something I actually saw at an IMAX first. And it was really cool. Caught my eye. So much so that I said, wow, I could use that in my classes. And wow, I guess I'll buy the DVD. There were still DVDs back then. Damn, did this mess up again? I was recording my opening day thing for them the other day. It's not recording, though. Have you been recording the whole time? Click.